In this unit, we're going to be doing a study of chemical bonding. To do so, we'll perform a short introduction to the nature of a chemical bond, and we're going to start with an emphasis on covalent bonding and how it determines molecular shape using two theories of bonding: valence bond theory along with hybridization, and valence shell electron pair repulsion theory, or VESPER as it is known in short. So bonding in general. Consider what happens when two hydrogen atoms approach. So we are going to look at the case when two unbound hydrogen atoms, so there's one hydrogen, and it's coming closer to another unbound hydrogen atom right there. Okay? And what I mean by that is that these are hydrogen atoms that have not bonded together yet, right? So each hydrogen atom has one electron, and they are not yet joined in a covalent bond. So we're going to take a look at the forces, and we'll look at what happens to the forces as the atoms get closer and the impact on potential energy. So as the two atoms come closer together, we have increased repulsion between the two nuclei, because the protons in each of the nuclei of the hydrogen atoms get closer together, so that force increases. So we'll write right here, increases. And the impact on potential energy, as that force increases, as we try to push together two objects which are repelling each other, the impact on potential energy is that potential energy increases. Okay, so as they get closer, there are greater repulsions, so we have increasing potential energy, right? Because the tendency is for them to be further apart as a result of these repulsions. As the electrons get closer, their electrons will also repel, right? So the force increases. Those electron-electron repulsions, those forces also increase. And the impact on potential energy is yet again another increase. Potential energy increases because the electrons from the two atoms are repelling each other. Here, what happens to the force as the atoms get closer? Well, the nucleus of one atom is attracted to the electron of the other atom. So the nucleus of this atom is attracted to the electron here, and so that's actually going to pull them together. And similarly, the nucleus of this atom is attracted to the electron on that atom, and that will pull the atoms together. So the electron to nearby proton attraction also increases, and that's a pulling force. That's not a repulsion force. And because that's a pulling force, the potential energy there decreases, right? Because it's moving towards, it's moving with the attraction, not against the attraction. And then the electron to its own proton, that has no effect. So that's not affected. The electrons, what that means is the electrons in this atom are still attracted to the protons within their atom. That doesn't change as they get closer together. Okay, so what happens is as these atoms get closer and closer together, and we see it in this diagram right here. Here are my two unbound hydrogen atoms. As they get closer together, the repulsions increase between the nuclei, the repulsions increase between the electrons, but then there is the increased attraction between the proton of one atom and the electron of another. So as they get closer together, yes, there is an increase in potential energy, but then there is also a decrease in potential energy as a result of the attraction between the protons of one and electrons of the other atom. So what we're seeing here is, as the two atoms get closer together, we see that there is a decrease in potential energy. this is still not the correct distance for these two atoms to form a chemical bond, because they have not gotten close enough together. Once they get to this distance, as denoted by the number 3, the repulsion forces pushing these two atoms apart are perfectly balanced with the attraction forces between the protons here and the electrons here, keeping the atoms together. So at this distance between these two nuclei, you have a perfect balance of repulsion between these two nuclei, repulsion between the electrons, and also the attraction force between this proton and the electron here, and vice versa. So this is the perfect distance for when a chemical bond will form. If the atoms get too close together, well, that's not a good distance for a chemical bond to form, because if they're too close together, those nuclei will repel too much, and the electrons will repel too much. And so the repulsion forces will dominate, and at this distance, a chemical bond cannot form. And as we push them even closer and closer together, we can see that the potential energy continues to go up. This is not ideal for a chemical bond to happen. We want a chemical bond to happen at the lowest possible potential energy, and that happens at an internuclear distance of 74 picometers. That means the distance between these two nuclei is 74 picometers, and that's when a chemical bond will form, because both the attraction forces and the repulsion forces between these two atoms are balanced out, so enough to allow a covalent bond to form. So let's just quickly make some notes here. At distance 1, right here, no chemical bond can form, so no chemical bond can form. And when I say chemical bond, I mean covalent bond, but no covalent bond can form because the atoms are too far apart. Okay. That is the case for 1. That is also the case for 2. These atoms are still too far apart for those attraction forces to be sufficient. At 3, at the distance of 3, this right here represents the ideal distance between atoms to form a covalent bond, since attraction and repulsion forces are balanced. Okay, so at this distance right here, you will form a covalent bond between two hydrogen atoms. If we try and get closer, again, this is too close, repulsion forces dominate. So in this place right here, we say at distance 4, repulsion forces are too strong. So the atoms have to be at this distance to be able to form a covalent bond. Okay, moving down. When atoms are at an average bond length apart, we'll just repeat what we previously said. When atoms are at an average bond length apart, so this is an average bond length apart, both attraction and repulsion forces are balanced, and a chemical bond can form. Okay, it is at the lowest potential energy that you have a covalent bond form. The first theory that we're going to look at here is called the simple valence bond theory. And simple valence bond theory has to do with how these covalent bonds form. Well, the simple valence bond theory states that partially filled orbitals will overlap. And so what we mean by partially filled orbitals, just to make a side note, is orbitals that are only partially filled. So they don't have a counterspin electron within the orbital. So these partially filled orbitals will overlap with each other. Which then completes the electron pair. And once we have an electron pair, as you recall, this results in a covalent bond. This leads to a decrease in potential energy, resulting in the formation of a chemical bond. Okay, so it says this leads to a decrease in potential energy, resulting in the formation of a chemical bond. Okay, we are going to show some work on what that looks like. So if we look at hydrogen, we're going to show the valence shells at the ground state. Recall, the valence shells are the highest N value. So if we think about hydrogen, hydrogen's highest N value, well, it's just 1, right? And so it just has a 1s right here, and another hydrogen here has a 1s, like that. And so what happens is the 1s orbital of this hydrogen atom will overlap with the 1s orbital of this hydrogen, and you end up with a covalent bond. So we will write this overlaps to complete the pair. So if we were to sketch this out, what we would see here is we would see a 1s orbital, which looks like a sphere, overlapping with a 1s orbital over here. So this is your hydrogen, that's your 1s, and this is another hydrogen, it's 1s. And in the middle here you have your paired up electrons. The textbook and other diagrams do a much better job of showing what an overlap would look like. It won't be this sort of two overlapping circles. Rather, you get a larger overlapping region of high probability of finding the electrons that have now bonded, right? So these two 1s orbitals overlap, and this is the resulting overlapped orbital, right? This shape represents the high probability of finding an electron within this 3D region. So the description of the bond here is that we have s orbitals and s orbitals overlapping to form what is called a sigma bond. And a sigma bond is effectively a single covalent bond. So these two 1s orbitals overlap to form a sigma bond. So what if we don't have a 1s and a 1s overlapping? Well, let's take a look at this example. This is hydrogen fluoride. And so what we have here is we have on one side we have the hydrogen, on the other we have the fluorine. So what we'll do is we'll put hydrogen right here, and we have its 1s orbital right there. And then we have fluorine, and we're looking at its valence shell, and the highest N value for fluorine is 2. So we look at its valence shell. So it's 2s and 2p. We don't look at the 1s because that's the inner shell. So we do here 1, 2, and its 2p looks like this. And it just has the single electron here, plus the single electron of the hydrogen, and as you may have predicted, the p orbital from the fluorine will overlap the s orbital from the s, and you basically get an sp overlap. And so we'll sketch that out so that you can see it and as you would present it on an assessment. So this is your hydrogen and your 1s. Then you have fluorine. And fluorine is not an s orbital. We saw that overlaps. It's a p orbital, and p orbitals generally look like this. And so you have these two lobes here, and the overlap occurs like this. Because there is overlap between an s and a p, this is s, that's p, the resulting bonded orbital will look like this. Okay, so this is the resulting shape of when you overlap an s and a p. So in this shape, you have contained the high probability of finding an electron in those bonded electrons. So within that chemical bond, this is the location that you are more likely to find an electron. And as you can see, it's basically a shape that combines the shape of the p along with the characteristics of some of the s, because this side is a little bit more spherical. So we would call this one s and p. They overlap to form, again, this is just a single bond between hydrogen and fluorine, so to form a sigma bond. Finally, looking at the next type of bonding between overlapping orbitals is, say we had fluorine bonding to itself. So we have the molecular fluorine, right? So we have fluorine here. We have its 2s and its 2p. And then we have another fluorine with its 2s and its 2p. And what happens is the p orbital of this fluorine will overlap the p orbital of that fluorine, and you end up with p to p overlap. So here is one fluorine, and that will overlap with another fluorine. And so you have p to p overlap right here. Okay. So that's your 2p. And that's your 2p. I'll go back and I'll relabel this in as well. That's your 2p. Again, when you have this p and p overlap, what you end up with is a larger region between the two nuclei of high electron probability, right? So we have p and p overlapping to form a sigma bond. Okay. Now, it is important to note that the p to p overlap here is end to end. And what I mean by that is that one end of the orbital overlaps with the end of another orbital to make the sigma bond. Because in the next example, we'll see what happens when they overlap side to side. The next one is a little bit tricky, and it requires thinking a little bit again in 3 dimensions. We will have oxygen right here, and oxygen, its valence shell is 2s and 2p. And we have another oxygen with 2s and 2p. I'll fill these up. Okay. And as you can see here, we're going to have 2 different p orbitals overlap. We're going to have one p orbital overlap, and we're going to have another p orbital overlap. So how do we draw that? Well, here's the deal. You have oxygen in the middle, and you will have a p orbital here overlapping with another p orbital over here. Okay, so here are your 2 electrons that have overlapped. That is, we've got a p orbital from this oxygen overlapping with a p orbital from that oxygen. Now the issue is we need another p orbital to overlap with another p orbital. Remember that p orbitals have 3 orientations in space. So what I would say is, let's say that there is an x-axis along here. So that is a 2px, and that is a 2px that have overlapped. Where am I going to get this other 2p? Well, like we said, 2p's also exist along the y-axis. So we have a 2py, and we have a 2py here. So what will end up happening is these x to x's, these 2px's will overlap end to end, but then these 2py's will overlap this side with this side, and you get what's called side to side overlap. So the bottom here also will overlap with this side as well, and you get side to side overlap. Let's just write that in. That's side to side. And because my diagram is obviously lacking, right, I took this from the textbook, and as we can see here, this is a better diagram of the side to side overlap between the 2py orbitals. What ends up happening, the resulting shape when these orbitals overlap side to side, is that the electron probability regions end up becoming above and below the bond axis, right? And what we mean by bond axis, oxygen is bonded to oxygen, so that's your bond axis, and this side-to-side overlap produces basically this lobe, this big lobe up here, and a big lobe down here. Okay, so this is your side-to-side overlap, and this is what we call not a sigma bond, but in fact we call that a pi bond. To be clear though, the bond in the middle here between these two oxygens is still a sigma bond because that is end-to-end overlap, but the side-to-side overlap is what is called a pi bond. And we see it right here. So one pi bond consisting of regions of electron density above and below the bond axis. What I tried to capture here from the textbook is what we would see. We would see effectively, this is an oxygen nucleus, and this is an oxygen nucleus, And between the two oxygens, we would have our sigma bond as a result of the 2px overlapping end to end with the 2px, right? So this one right here, that's my end to end. But then above and below this bond axis, we have the pi bond, right? And that is the result of the side-to-side overlap. Okay, so if we have two bonds here, this is, as you may recall, called a double bond. So a double bond, in fact, it comprises of a sigma bond and a pi bond. Okay, so I'll just write that in here. Okay, so you have P and P, end to end. And that P to P, end to end, that is your sigma bond. But then you also have P and P side to side, which is your pi bond. So in a double bond consists of a sigma and a pi. Last one is a triple bond. And again, this involves thinking in 3 dimensions here. Although, if I was to be clear, this is actually really just 2 dimensions. But let's think about 3 dimensions in this case. 2s, 2p, and here is 2s and 2p. Okay, so as you have seen right here, we're going to have a bond here and a bond here. So we will have here a triple bond. And so what this will look like is you have your nitrogens in the middle, and you have your p orbital here and your p orbital here, and you have the end-to-end overlap that produces that sigma bond, right? Okay, we'll call this one 2px. That's 2px, and that results in your sigma bond. Then you also have up and down your 2py. And those 2py's, as we saw above here, they will be a side-to-side overlap, resulting in a pi bond, right? Where is the other p orbital? Well, you may recall that the other p orbital is the 2pz, which is coming out in front and hiding behind like that. So it's coming out in front and hiding behind. And so this one will also undergo end-to-end overlap as well, resulting in yet another pi bond. And we can see that right here. Look, they've chosen to put 2pz vertically, and that's fine. So you've got 2pz vertically. So these undergoing, and these 2pz's undergoing end-to-end overlap, right? That's a pi bond. And then the 2py's, which are coming forward and backwards, they will also undergo overlap, which results in a pi bond as well. And recall that we still have the sigma bond from the end-to-end overlap. So the types of overlaps that we have here is that we have P to P, end to end, resulting in my sigma bond. I have P to P, side to side, twice times 2, resulting in 2 pi bonds. So as you can see, a triple bond consists of a sigma bond and 2 pi bonds. To summarize the properties here, we find that sigma bonds are located in, your single, double, and triple bonds, because we have sigma bonds and single bonds. But we also saw that they exist as well in double bonds. And we have also seen that they exist in triple bonds as well. Whereas pi bonds exclusively exist in double and triple bonds only. The orbitals that overlap to produce sigma bonds are s and s, s and p and p, end to end. Whereas the bonds the overlaps, the orbitals that overlap to produce pi bonds are p and p when they go side to side. The areas of electron density in the bond, well, if we take a look over here, as we can see, the areas of electron density are between the two nuclei, so they are along the bond axis. Whereas for pi bonds, we saw that if this is the bond axis, the pi bonds exist above and below the bond axis, or side to side along the bond axis. So we write above and below the bond axis. Rotation of the bond, sigma bonds, so single bonds, can rotate. So these sigma bonds rotate. However, when you have a double and a triple bond, pi bonds do not rotate. So only sigma bonds can actually rotate. So the atoms can rotate in the bond, but in pi bonds there is no rotation. This concludes an introduction to the basics of covalent bonding. We started by looking at when covalent bonds form, and that's when the atoms have formed or have found the ideal distance where repulsions and attractions are balanced out. Then we looked at simple valence bond theory and showed that orbitals overlap to complete the pair and result in both sigma bonds and pi bonds. And then we finished by summarizing the properties of both sigma bonds and pi bonds. Okay, great. Thank you for watching.